So let's start this lesson by writing down a sequence of numbers. So here's 1, 3, 5, 7, blank, blank. And your job is to fill in the blanks. So hopefully you can solve this mystery and come up with 9 and 11. And the reason you knew that so quickly is because you probably recognized that these are odd numbers. But you may not have recognized, or you may not have thought, that what's actually happening here is we're doing 1 plus 2, 3 plus 2, 5 plus 2, plus 2, plus 2, on forever. That's where these numbers are actually coming from. You know this is a pattern of odd numbers. So I'm going to write down a little different pattern that maybe you've seen before, maybe you haven't. 1, 1, 2, 3, 5, 8, blank, blank. So go ahead and write that down. Take a second and see if you can figure out what the pattern is. Go ahead and pause it. All right, so if you did figure out the pattern, you would have got 13 and 21. Okay, now don't feel bad if you didn't figure it out. Okay, it's not something that you've been exposed to before. It's not a kind of thinking that you've been expected to do, but you're going to be expected to do it for the rest of this year. The pattern that you see here, or that you will see after I explain it to you, is that we start with the number 1, and then we add whatever came before it. Now, nothing came before it, so 1 plus nothing is just 1 again. Then we take this 1 and we add what came before it. So 1 plus 1 is 2. We take 2 plus the number that came before it. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. 13 plus 8 is 21. And we could continue this forever. This is a really important and really popular sequence of numbers. Don't kill me on the spelling of this, but it's called a Fibonacci sequence. Okay, and it's a popular sequence of numbers in math. It has all kinds of applications. If you're one of those people that always wants to know, well, where am I ever going to see this? Well, go outside. You'll see this everywhere. And if you want more explanation of that, come see me. I'll show you some pretty cool stuff. But what we're going to talk about and what we're going to do with these kinds of sequences that we're figuring out is something called inductive reasoning. Okay? And inductive reasoning is simply reasoning that something is true. So you're going to reasoning just means thinking or figuring out. So you're going to figure out that something is true based on specific cases. So what we observed here is that 1 plus 2 is 3. 3 plus 2 is 5. 5 plus 2 is 7. So we make an assumption that we can just continue that pattern. So inductive reasoning is really observing a pattern. If you see the phrase or the words, observe a pattern, that's a dead giveaway that this is inductive reasoning is what's happening. All right, but when we observe that pattern and we write it down, so we wrote down that this is the pattern of odd numbers, or this is the Fibonacci sequence, or we may have said that we add each term to the previous term. Okay, that's basically what we did with this Fibonacci sequence. All these things that we're writing down, these are called conjectures. Okay, conjecture. And a conjecture is a statement you believe to be true. Now, it doesn't have to be true. And you'll see in a minute, we're going to do something that aren't even close to true. But it's a statement you believe to be true based on inductive reasoning. So some of you, a minute ago, came up with different numbers here than what I put. And you probably had some kind of system worked out in your head where they came from. Now, that was a conjecture that you made, and you believed it to be true. Now, obviously it wasn't, but that's okay. That isn't, you don't lose points for that, right? You came up with a conjecture. We tested it, and we found out that this is actually the conjecture that's true, but that's okay. So we'll do a little example of how we're going to use this. So here's an example of using inductive reasoning. All right, so you may see a problem, in fact you will see a problem, that says the product of an even and an odd number is blank. Okay, so write that down. And this is an example of inductive reasoning. You're not going to discover that the product of an even and a non-number is 6, or that it's 15, or that it's happy face, or unicorn, or anything like that. There's not an answer that goes here like a typical math problem. The answer that goes here is something that you're going to come up with by using inductive reasoning. So there's 2 steps to inductive reasoning. So step 1 on a problem like this is we list examples. So I'm going to list out some examples here of what this is saying. It says the product, which means multiply, of an even and odd number. So I'm going to list out an even and an odd number. Multiplied together, their product is 6. So right now I see these things. I'm going to observe that several things I've observed here already. An even and odd number equals 6. An even and an odd number is even. An even and an odd number is positive. An even and an odd number is divisible by 3. Okay, there's lots of things, right, that I've observed here. But I only have one little example. So that's not really enough for me to make a conjecture. So I'm going to go with a couple more. So here's another even odd number. 4 times 1. Okay, so is that 6? No. Is it even? It's still even. Is it positive? Still positive. And is it divisible by 3? No. So I'm kind of limiting down my options pretty quickly, right? So I'm gonna guess, or I'm gonna predict that no matter what I keep doing, as long as I do even and odd, it's gonna come out even, because I don't see any reason why that pattern would change. But the positive part, I think I can do something about that. So I'm gonna do -2 times 5. Even times odd, -10. Now that's still even, right, as I predicted, but it's not positive. So if it's not positive, the only thing I have left is even. So now some of you are going to moan and groan about this, but step 2, you're going to complain about it. You say, do I have to? Do I have to do that? Yes, you have to do it. And the reason you have to do it, you don't need to look any farther than your previous 2 test scores. Okay? If you had done things the way I told you on those, you wouldn't be in the situation you're in now. Make a conjecture. That means you're going to write out a statement that says what you believe to be true. And what I believe to be true here is that the product of an even and an odd number is even. And that is my conjecture. That's a statement I believe to be true based on inductive reasoning I did. So we're going to go do one more example. And again, I don't know how much space you've taken up on your paper, but when I make these videos for you, I'm intending this to be 1 page. So if you're writing humongous, if you're taking 15 lines of paper to write 1, 2, 3, 4 lines of stuff, you need to get that under control. Okay, you're wasting paper. This is a one-page set of notes. All right, the next example, you're going to see instructions that say, show that the conjecture is false. Okay, so I'm going to write down a conjecture. This is a conjecture. It's a statement that somebody believes to be true based on inductive reasoning. The statement is, for any real number x, so any number I pick for x, x squared is greater than or equal to x. So this right here is a conjecture. It's a statement that somebody believes to be true based on inductive reasoning. Well, we're going to try to prove that it's false. Let's say I came into class tomorrow and I said everybody in this room is wearing a red shirt. How many of you would have to be wearing a different color for my statement to be false? Okay. This is called a counterexample. And as you probably thought about the shirts, we only need one counterexample, right? If I said you're all wearing red shirts, Susie stands up with a blue shirt on, guess what? Mr. Lewis is a liar. Everybody's not wearing a red shirt. So we need to come up with one real number that when we plug it in for x in this little scenario, it comes out false. So let's pick some numbers. And I'm going to give you a hint. We're not going to use all these numbers, but these are numbers that you should always pick from. Okay? These are good numbers to pick with. Don't pick 37. Don't pick 65.2. Pick these numbers. All right, so let's start out and say that x equals 2. Well, 2 squared greater than or equal to 2. I'm just plugging it into this. I get 4 is greater than or equal to 2. Well, that's true. So we'll try some other numbers. Let's try x equals 1. So 1 squared is greater than or equal to 1. So 1 is greater than or equal to 1. Well, 1 is equal to 1, so that's good. So I'll keep trying. Try 0. X equals 0. 0 squared greater than or equal to 0. 0 times 0 is 0. Is 0 equal to 1? Yes. So no good there. So I just keep going with numbers that I know. So I'm going to skip -1 just because, I know what that's going to be. So I'll do -2. -2 squared is greater than or equal to -2. Well, -2 squared is positive 4. If you're using a calculator and you don't put these parentheses, your calculator will lie to you. Is 4 greater than or equal to -2? You bet. So we could keep going with this forever and never come up with a number that when we plug it in is greater than or equal to what it was. But a real number is any number you can think of. So any number you can think of in your head right now. How many of you thought of this number? Let's plug that number in and see what happens. Remember, when you multiply fractions, go straight across. 1, 4. So 1/4 is greater than or equal to 1/2. Is that true? Definitely not. So x equals 1/2 is a counter example. All right. So that's it. See you tomorrow.